Greetings to all my fellow grade 12s. Okay, greetings officially, since we started recording this video. Obviously, we didn't have a lesson last week, okay, mentioned that, but we have a lesson this week, and on Friday, we will be making up our lesson from last week that we missed as well. And this week, Friday, will be the last Friday that we will have a session. Okay, it will be the last Friday that we will have a session. Okay, possibly for the rest of the year. But I'm on the education.gov.za website under the curriculum tab under the for the NSC, National Senior Certificate, grade 12 examinations, and there is a lot of examinations here from 2008 November, FEB Marches, and all the way through to May, June as well, up until the latest November, which was last year, 2020 November paper. So I'm going to be making use of this quite a bit in our sessions this week and this year also, because it's very important that we practice past papers frequently. Obviously, I won't show you all of them because I need you guys to also engage yourself. So if I show you guys all the papers, then you guys are going to have no papers to practice from, because you know how it looks and you've seen it before and your brain is familiar with it. I don't want to create too much familiarity. I'd like for your brain to see something new and adapt to solving a question at face value. Okay, what I will do is I'll start from 2017. And I'll take the 2017 FEB March, which was obviously the examination set of exams before the 2017 November. So 2017 FEB March was the supplementaries of 2016. We're just going to scroll through until we find physics at the bottom here. There we go. And we're going to take paper 1. I'm going to open it in a new tab. Here we go. Okay. While I'm waiting for it to open. Okay, there we go. I'm going to dismiss to open it in Acrobat, and I'm going to zoom in slightly. Okay. Let's just check what we have there. Question 5, I think. Okay. Okay, cool. So let's actually just zoom out a little bit to 100 so we can get that first question in. What I will do about power first is, as we can see, the first question in question 5 of 2017 FEB March is the question is define the term power in words. Okay, so what we're going to do is I will at least define what power is in words. Okay, so let me just make sure I can have a decent layer here. There we go. The term power, as defined in words, is basically the rate at which work is done, or basically also the rate of energy transfer. Okay, that is basically the definition for power. Okay, so basically the formula, there's actually more than one, so I'll say formulae, but just from the definition alone, power, capital P, is equal to the rate at which work is done, so that must be W for work over delta T, because the word rate means per time or per second. Okay, so the rate at which work is done. Okay, the SI unit of power is in watts, W-A-T-T. Okay, watts. Okay, 1 watt is basically equal to 1, let me take that dot away there, add in the number that's written like this, or in fact let's just leave it as it was, 1 joule per second. 1 watt is basically the same as 1 joule per second. Why? Because obviously work is measured in joules and time is measured in second. 1 joule per second, 1 watt. So power, whenever we talk about watts, we're talking about power. Okay. And then we also have power also in terms of velocity as well. Okay, that another formula for power is that the average power is equal to the force times the average velocity. Okay, but I will show you that formula in a question, of course. Okay, so let's have a look at the question again. This is question 5, I think. Here we go. Question 5 just asked to determine, and then 5.2.1 was calculate the gravitational force, etc., etc. So I want to check question 4 quickly. Yes, question 4 is your momentum question, so it's not that. And question 6 is your another question, another section question. Okay, so let's go with cool. Question 5, a lift arrangement comprises of an electric motor, a cage, and its counterweight. Okay, the counterweight moves vertically downwards and the cage moves vertically upwards. The cage and counterweight move at the same constant speed. Refer to the diagram below. Okay, cool. The cage carrying passengers moves vertically upwards at a constant speed, covering 55 meters in 3 minutes. The counterweight has a mass of 950 kgs. The total mass of the cage and passengers is 1,200 kilograms. The electric motor provides the power needed to operate the lift system. Ignore the effects of friction. And so 5.1 would be this definition here. Okay, rate at which work is done. Pretty easy. 5.2 is what I'm interested in you guys doing, and I will take you all through 5.3, which is calculate the average power in required by the motor to operate a lift arrangement in 3 minutes. Assume there are no energy losses due to heat and sound. All right, so let's do 5.2. I'll give about 5 to about 6 minutes for 5.2 because it's work we have already done. Let's have a look at the solution there. It says calculate the work done by the gravitational force on the cage. Okay, well, let's go to the solutions here quickly. Let's take this away here. Cool, this is question 5, and this was of 2017 FEB March paper 1. I like just to know exactly what we're doing. Cool. And so the first one though was the work done. So it's work. So the work done by the gravitational force is WG is equal to 5.1, which obviously the force of gravity multiplied by the delta x by cos of theta. Okay, remember this is vertical motion. So that is basically mg, now actually delta y. Okay, cos theta, remember it's vertical motion. Okay, so the work formula should just be like that, but the work done by the force of gravity therefore must be equal to this, of course. So we know the mass of the lift, I think elevator was 950, or am I missing something? The counterweight mass has a mass of that, the cage and passengers. Okay, cool. So that is not 950, sorry, that is the wrong mass there. So that's 1,200, which is of the elevator, times 9,8. Delta y is 55, of course, and it's cos 180 degrees. Okay, let's check y. So the calculate gravitational force on the lift. So the lift is going. The counterweight moves vertically down and the cage moves upwards. and they want the force on the cage. So the cage is moving upwards, and obviously the force of gravity is going down. So obviously delta y and the force are in opposite directions. That's why it's cos 180. So we're just going to pop this in on a calculator. 1200 times 9,8 times 55 times cos 180. And that should give us an answer of minus 646,800 joules, which is also negative 6,47 times 10 to the power 5 joules if we put that answer in scientific notation, whichever one your calculator gave. Okay, so this is the answer for 5.1. 5.2, they asked, of course, what was the work done by the counterweight. So the work done by the counterweight, I'm just going to call it CW, counterweight. WCW, because I don't want to use just C, because that could be, the marker could read it as a conservative force, which is not, of course. So it's also the same formula, so I'm just going to use mg delta y cos theta. So that's 950 times 9,8 times 55, of course. The counterweight's going down in the same direction as the force, so of course this is going to be cos of 0. And then that equals to, if I put that in my calculator, 950 times 9.8 times 55 times cos 0. Cos 0 is 1 anyway, so that gives me an answer of 512,050 joules, which is, if you got a scientific notation, answer 5,12 times 10 to the power of 5 joules as well. Okay, so I just want to check. We got that one right. These two correct. 5.3 now is the power question. Calculate the average power required by the motor to operate the lift arrangement in 3 minutes. Assume that there are no energy losses due to heat and sound. No energy lost at all. Okay, so there's a couple of ways that we can do this. We can either use the average power formula, or we can use the normal power formula. Doesn't really matter. Okay, so what's important to note here is that if we're going to say W net equals to the change in EK. Now, if there's no energy lost, that means this is going to be equal to 0. So in other words, the work done by the force of gravity plus the work done by the counterweight is basically going to and plus the work done by the motor, which we haven't calculated yet. That's basically must equal 0. Now the work done by the force of gravity, okay, was negative 646,800 joules plus 512,050 joules was the force of the work done by the counterweight, plus the work done by the motor is all equal to 0. Okay, basically that's negative goes over, so the work done by the motor is equal to 646,800 minus 512,050, and therefore the work done by the motor is equal to, I think it's 134,750 joules. Yes, that's correct. Okay, so because remember, again, for the question, they said calculate the average power required by the motor. So you need to know, of course, what is the work done by the motor. So then we come over here, pick another color. The power equals to W divided by delta T, which is obviously going to be this 134,750, which is the work done by the motor, or the energy transferred, the rate of energy transferred, or the rate at which work is done, or the work done, divided by 3 minutes, so that's 180 seconds, and therefore the average power by the motor is 748.61 watts. That's using the normal power formula. Other option is saying, well, power average power, because the question was specifically average power, is equal to the force multiplied by the average velocity. Okay. So now how this option is going to obviously work. Okay. Think the formula for velocity, alright, that we learned in grade 10, velocity equals delta x divided by delta t. Or in this case, because it's vertical, delta y divided by delta t. Okay, now watch this. Okay, and this was also for VAV that we learned in grade 10. So if you haven't remembered it from grade 10, I'm jogging your memory now. Okay. First things first would be to obviously have a look at what is the net force. Okay? That would be the first thing to do, as what is the net force. So, 1,200 times 9,8 is going to give us a net force of about, just check, yeah, let me check. Sorry guys, hold on a second. The force of gravity of the cage. No, that's wrong. That's FG 1,200 times 9,8. Yes. Okay, so I don't know where they're getting that from. And 950. So I must just make sure of my calculations here. Yeah, that's right. So in order for you to get that, you need about that. Okay, cool. Just check the numbers in the equation. That's 1,200. Okay, cool. So what you can do for the force now, remember the net force basically that you're going to have here, because you've got forces of two things now happening here. You've got, of course, 1,200 multiplied by 9,8 as 1. Okay, because the cage is going up. Minus, of course, 950, that's going down, times 9,8. Multiplied, of course, by average velocity, which is 55 divided by 180. 55 meters, of course, delta y, and time 180 seconds. And then, of course, your average power that you're going to get is, of course, so it's working out the net force there, 1,200 times 9,8, okay, minus 950 times 9,8 gives you an answer of 2,450, and 2,450, that's multiplied by 55 divided by 180. It gives you the same answer as 748.61 watts. Okay, so I have another question paper for you. This is the same year, 2017, but it's the May-June. It's the adult matric paper, and this is also question 5. And let's just read the question together. It says the diagram below shows a boy skateboarding on a ramp which is inclined at 20 degrees to the horizontal. A constant frictional force of 50 newtons acts on the skateboard as it moves from P to Q, which we see outlined in the diagram there. Consider the boy and the skateboard as a single unit of mass 60 kilograms. Ignore effects of air friction. 5.1, draw a labeled free body diagram showing all the forces acting on the boy's skateboard, which is obviously we're taking that as one object now, until unit while moving down the ramp from P to Q. Points, that's 5.1. Before we get 5.2, it says points P and Q on the ramp are 25 meters apart. The skateboarder passes point P at a speed vi and passes point Q at the speed of 15 meters per second. So we don't know what is the initial velocity, but we do know the final. Ignore rotational effects due to the wheels of the skateboard. 5.2, state work energy theorem in words. 5.3, use energy principles to calculate the speed of skateboard of the skateboarder at point P. So that's about 11 minutes worth of work, surely. So possibly a little bit less if we are efficient and we write a bit quickly. So I'm going to assign that amount of time, 11 minutes. So at about at 1:15 I'll check in where we at about 1:15 I'll check in, and just before 20 past we'll have a look at the question, because we still got 5.4, which is calculate average power dissipated, but we'll take time to do that. We'll first focus on we'll first focus on 5.1 to 5.3, and then we'll do 5.4. Okay, let's go. Alright, so this is the May-June paper, 2017, paper 1. And question 5 again. 5.1 was draw the free body diagram. So, of course, very easy. It's just a dot like that. Gravity, of course, goes straight down from where he's standing. Okay, and of course, the when he starts rolling down the ramp from P to Q, obviously, the normal force is going to go over here. Well, that was a very bad line. Force goes over here, and of course, friction now goes in the opposite direction. Force of friction. Okay, so that was the free body diagram, 3 marks. Okay, please tell me we all got the free body diagram correctly. Please, somebody please tell me that that is the case.
Yep.
Fantastic, awesome. The next question. Ooh, someone sent me a text. Good, awesome. The next question was, after a bit of information, they state work energy theorem in words. I'm not going to write it down because we all know it. It is the net or total work done on an object which equals to the change in the object's kinetic energy, which is straight from the formula W net is equal to change in EK. Or the work done by the net force equals to the change in the object's kinetic energy. Okay, but the first one obviously is what we understand and know the most, which is, of course, the network, or the network done on an object is equal to the object's change in kinetic energy. All right, 5.3, which is why I didn't write it complete here. 5.3's question was to determine the initial velocity. There's a couple ways that we can obviously do this. Okay, so of course we use the same formula though, energy principles. W net is equal to the object's change in EK. Okay, so what's important here to note is find out what is the work done by the force of friction, of course, plus the work done by gravity parallel. Okay, which is the only two forces that would obviously, sorry, that's W there, would obviously act on the boy to skateboard unit. And of course that would be, let me see, am I correct in saying this? Yes, I am correct in saying this. Okay, and then that is equal to half mvf squared minus half mvi all squared. Okay, so this would be f delta x cos of theta plus fg parallel delta x cos of theta. That would equal to same thing, half mvf squared minus half mvi all squared. So let me just check if there's anything I am missing in the question. Fantastic, 100%. So that would be, they said it was a 50 Newton frictional force, so it's 50 times 25, because it's between P and Q, times cos 180 degrees, plus, of course, this is mass times gravity, sine theta, FG parallel, so that's the mass, which is 60, times 9,8, times sine of 20 degrees, delta x, 25, cos theta, so that's cos 0, so that's just 1, and that equals, of course, to half of 60, and I'm just going to factor out half m, so half of 60 times VF, which is 15 squared, minus VI all squared, which we still do not know. Okay, I seem to have run out of space here, so I'm just going to make sure we all have that. I'm just going to take a, no, actually I don't need a screenshot. Okay, cool. So let's go to the next layer. So that's going to equal about, let's just use the top here, minus 2,000 or minus 1,250 plus 60 times 9,8 times sine 20 times 25. It's about 5027,696. I'll use 3 decimal places to get a more accurate answer. And that would be equal to half of 60 is 30 times 50 squared, 6,750, minus, of course, 30 VI all squared. So let's do this. Minus 1,250 plus 5,027,696. That's going to give me 3,777, and then I'm going to take that over. Let me see quickly, which is the best way to do it. Okay, let me just write this. 3,777,696 is equal to this whole shebang. Okay, cool. So I'll swap these around. So I have 30 VI all squared is equal to 6,750 minus my answer. And I get roughly about 2,972,304. Divide both sides by 30. I get VI squared is equal to 99,0768. I'm going to square root both sides. And therefore VI is equal to 9,95 meters per second. Question 5.4 now says calculate the average power dissipated by the skateboarder to overcome the friction between P and Q. Okay, so let's just see how well you guys do with this one in the next 4 minutes, and then I'll mark it. So the average power dissipated for 5.4. So they want to know by the frictional force. Okay, so there's a couple ways we can do this. Okay, so another way to calculate average velocity is also to say that the average velocity, okay, literally, when you try to take the average of anything, you add it together and divide it by 2. So we calculate the initial to be 9,95. We found that the final was 15. And we divide it by 2. Okay, and if we do that, let's just put that in on the calculator. 9,95 plus 15 divided by 2. We'll get about 12,475. As the average velocity here. So PAV is equal to the force times sorry, that must be VAV times VAV. Okay, and that's obviously the force is the frictional force, so that's 50 multiplied by 12,475, and then therefore the average power that's dissipated between the that section PQ is going to be about 623.75 watts. Okay, now there is of course another way to do this. Okay, simply say, well, P also equals W over delta T. Okay, so the power dissipated by the frictional force, okay, the power the power by the frictional force, of course, okay, is equal to the work done by the frictional force. So that must be F delta X cos of theta all over delta T. So now you might say, but we don't know what delta T is. Yes, but there's an equation of motion that says delta X is equal to Vf plus Vi divided by 2 multiplied by delta T. We found this thing over here, that delta X, in fact delta X was equal to 25, is equal to 12,475 times delta T. And if you must divide both sides by 12,475, you'll get it delta T to equal roughly about 2,004 seconds. Okay, so you want the power dissipated by the friction, so that's going to be 50 on top here times 25 cos 180, all divided by the time, which is 2,004. If we do that, can't remember what was the work done by the frictional force. Did we even get that? Well, we just have, well, we had a number for it in my calculator. I think it was 50 times 25 times cos 180 over 2,004. It gives us an answer of minus 620, well, not 6,2, sorry, minus 623,75, which therefore the power, that just indicates the direction. The power is now 623,75 watts, and of course that's in the direction of friction. Okay, but we're not going to give a direction, we just state it clearly like that. So the second option or the first option, whichever one you decided to choose, would have given you the correct answer there. Okay, the first one was way quicker, second one was a little bit more work. Okay, so we needed obviously to find time. Anyway, it doesn't really matter, we still got it anyway. Now you could have also used the force of the buoy, okay, to also find out that same answer, 50 times 25 times cos theta, and it would have given you the same answer, but I prefer doing option 1, which was the first one that we see up top here. Okay, so in this question, May, June 2018, there's no power question, but it's still an energy question nonetheless. I don't believe we have done this question. It doesn't look familiar to me at all. Might be, but it doesn't look familiar to me. It says a load of mass 75 kgs is initially at rest on the ground. It is then pulled vertically upwards at a constant acceleration of 0.65 meters per second by means of a light inextensible rope. Refer to the diagram below. Ignore air resistance, rotational effects, and mass of the rope. Draw label free body diagram. Okay, I think everything there is in this part is in the diagram. Draw label free body diagram. Name the conservative force acting on the load. Calculate the work done by the gravitational force. State work energy theorem in words, and then use energy principles or work energy theorem to calculate the speed of the load when it's at the height of 12 meters. This is 13 marks and we have 15 minutes left, so we can go for 13 minutes. Mark what we can. Probably question I will mark is question 5.3 and question 5.5 before we say good night at the end of the session. Cool. So I'll cut it a bit short. I'll give it about 10 minutes, so I have 5 minutes at least to go through these two questions at least. Right, let's go through the solution. 5.1, draw a labeled free body diagram. And this is 2018. May, June. Paper 1. So 5.1, a free body diagram of the load. Very easily. Of course, there's a there's tension going upwards, and of course going downwards is weight, or Fg. 5.2 question was, name the conservative force acting on the load. That was tension. Okay, tension was the was it a conservative or non-conservative? Non-conservative force, sorry, yes. 5.3 was, calculate the work done on the load by the gravitational force, all right, when it has reached a height of 12 meters. Okay, so the weight, or the work formula, W is equal to F delta X cos of theta. Okay, now the work done by the gravitational force is going to equal to mass times gravity times delta Y cos of theta, because it's moving vertical. And then of course that's going to equal to mass, which is 75 times 9,8 times 12, and of course gravity is going downwards while the load's going upwards, so it's cos 180 degrees. So we plug that straight into our calculator, and therefore the work done by the gravitational force is minus 800 or 8,820 joules. Cool. Let's half the page quickly. Let's just halve it. Okay, hope we all got that solution there for 5.3. That should have been pretty basic. Yeah, let's do that. Let's come up here in a different color. So 5.3, 5.4 was, of course, state work energy theorem in words, which is basically the net work done on an object is equal to the object's change in kinetic energy. That was pretty basic. Okay. And then 5.5, I can't remember the question, so I'm going to read it. Use the work energy theorem to calculate the speed of the load when it is at the height of 12 meters. Okay, so we begin. W net is equal to the change in EK. Okay, so W net, of course, we got the weight of tension plus the weight or the work done by the force of gravity, which is obviously equal to the change in EK. Okay. Okay, so what first things first that we need to do is we need to first find out what is the the force of tension. Okay, so with this option, okay, or for this route that we're going to take, we're going to have to take the this route. So we already know what this is. So now we need to come and see. Well, of course, the formula suggests. I'll do it on the right hand side. F net is equal to mass, or yes, mass times acceleration. So we know that's going to be tension minus mg. It's going to equal to 75 times 0.65, and this is obviously 75 times 9.8. Going to equal 75 times 0.65, and this is going to be tension. So let's just check this out. Put on my light because I can't see anything. 75 times 9.8, that's T minus 735, and that equals to 75 times 0.65, that is 48.75. Okay, so that's going to come over, and that's going to be a plus. Therefore, tension, in this case, this is going to be plus 735, is going to give me an answer of tension, 783.75 newtons is the force of tension here. So now I'll come here and I'll say, just block this off. that the work done by tension is going to equal to 783.75 multiplied by 12 multiplied by cos of 0 is going to equal 9,405 joules. Right, so therefore 9,405 joules minus 8,820, because as you can see at the bottom here, it's a minus. Okay, it's going to equal half of 75, just half of mass, and Vf squared, of course, minus 0 squared. Okay, so 9,405 minus 8,820 equals 585. And half of 75 is 37,5. So I have 37,5 Vf squared. So 585 divided by 37,5 gives me an answer of about 15,6. Vf squared is equal to 15,6. And we're going to square root that, both sides, and therefore Vf is going to equal to 3,949, so 3,95 meters per second. 3,95 meters per second is the, as the question was wanted to know, the speed of the load when it is at a height of 12 meters, okay, starting from the ground. That grade 12s is my presentation for this evening. Thank you so much for joining me on exam questions of Work Energy Theorem, or just energy in general. We looked at some power questions, explained power and how it's done. And thanks so much for joining me, and we'll see you in the next session.